Hey guys, and welcome back to this class, Data Science, Deep Learning, and Python Part 2. So in this class we're going to compare the progression of the cost function for the three cases of gradient descent: full gradient descent, batch gradient descent, and stochastic gradient descent. Because there is a lot of code that I copied and pasted in this example, I'm just going to walk you through it line by line. So we import all the usual stuff in the top part of the file, and from util.py we import get transform data, so we're going to use the PCA transform data. We're also going to import forward, error rate, cost, gradient of the weight matrix, gradient of the bias, and Y2 indicator. We're going to do logistic regression instead of using a full neural network, just to speed things up. So in the first line here, I'm getting the transform data. I'm taking only the first 300 columns. I'm going to normalize x by subtracting the mean and dividing by the standard deviation. And since transform data already shuffles the data, I can just take the last 1,000 samples and make that my test set, and then train on the other samples. So I convert ytrain into ytrain indicator and ytest into ytest indicator. And I initialize my weight and my bias. Notice that I want my initial weights to be pretty small, so proportional to the square root of the dimensionality. I found the learning rate and the regularization parameter before we started recording this class, and we're just going to do 200 iterations because I don't want it to take too long. So I do the weight update and the bias update using the gradient and regularization, and I also do a forward pass on the test set because I want to calculate the cost from the test set and then plot that. And on every 10 iterations I calculate the error rate and I record that as well. I also want to pay attention to how long everything takes, because you'll see that one of these is very fast and one of these is very slow. For stochastic gradient descent, I'm going to do pretty much the same thing, but we're only going to make one pass through the data since we need to look at every sample and update on every sample individually. But on each pass, we typically want to shuffle through the training data and labels. So I actually only go through 500 samples because it's going to be very slow to go through every single sample. We want to reshape X into a two-dimensional matrix. So if you use an array selector, you get a one-dimensional matrix, but that doesn't work when you pass it into the gradient function. We do a forward pass to get the output. We calculate the gradient and the weight updates using regularization as usual. And we only calculate the error rate once for every n/2 samples because it's going to go very slow. There are 41,000 samples. And then all the same stuff at the end. And for batch gradient descent, we're going to do the same thing. I set my batch size to 500, and I want to know the number of batches, so that's just n divided by the batch size. One sort of important calculation that always shows up again and again is how do you select the batch. So that would be the iteration number times batch size to iteration number times batch size plus batch size. So that's how you get the current batch for the batch you're looking at for J. We do gradient descent with regularization, and then we print every n/2 or n batches over 2. And then at the end we plot all these on the same plot. So let's try this. Okay, so you can see that stochastic batch gradient descent has hardly improved at all. So we need to do many more iterations to get an improvement doing pure stochastic gradient descent. If you look at full gradient descent, it appears to converge faster than batch gradient descent, but it also ran slower. Now if you zoom in to the cost function progression, notice that it's not quite smooth for batch gradient descent, whereas it's pretty smooth for full gradient descent, so it always decreases. And then if you zoom into stochastic, notice that this is also not smooth.